Alright, silly people, here's the situation. This time we're going to be taking this Gaussian elimination code from the book. It's just called gauss-elim.py, I think. And we're going to be modifying it so that it can do partial pivoting as well as actually just solving the set of linear equations. What is partial pivoting? It's whenever you are doing your process of Gaussian elimination, and you get to the diagonal element of the first row, and you notice that the magnitude of the leading element of the first row is less than the first term of a row below it. So if that happens to be the case, then you want to flip those rows. You want to make the first row equal to the second row and the second row equal to the first row. And then proceed as normal. And you check that every time you go down another diagonal element. And this is so that you can avoid dividing by 0 a lot of the times. And we're going to see that if we replace the leading term in the first row with 0, then the Gaussian elimination code doesn't work, of course, because you're setting div equal to 0 when m is 0, and then dividing by 0. So you're going to get infinities, and so it's not going to work. But if we can still have this 0 here and switch rows whenever we need to, we can still work this out. So we are going to, in practice, do it like this. We're going to create another for loop right before we start dividing anything. So for I in range m plus 1 comma n, so that we're running down every row except for the one that we happen to be on, or actually every row below the one that we're on. And we're checking if the absolute value of any of those rows below the leading element of that, if it's greater than the absolute value of the current diagonal element, then we want to flip the rows, right? To do this, I think in the least amount of lines of code that actually works, you make another for loop, this time in range n, and this is so that you run over every column of the rows that you're replacing, and you just make it so that, first of all, the jth element of the m row is equal to the jth element of the I row, but simultaneously make it so that the jth element of the I row is equal to the jth element of the m row. So that is doing this sort of like comma notation effectively is switching the values in the matrix. So a indexed m comma j is now equal to a indexed I comma j, and a indexed I comma j is now equal to a indexed m comma j, which is cool. And then after the for loop, you also want to make sure that you do the same thing. You flip the rows of the v list, which is what you're actually solving for. So it's very important that you make v indexed m comma v indexed I equal to v indexed I comma v indexed m. If we run this, we'll see that it still gives the same values. And if we replace the leading term with a 0 as per part B, you can still get results out of it whenever you do this. So it's a very powerful correction to the Gaussian elimination code. All right.